This video is brought to you by Michael Speaker and Maximilian Willert from SodiusWillert. In this video, we will show you how you can move class variables in your model from RAM memory into ROM as constant data and still initialize this constant data differently for each object. First, we would like to briefly explain when it makes sense to make data of a class constant. Object-oriented, you could represent a traffic light as follows. A class traffic light with three parts, red, yellow, and green, of the class lamp, which has the following four attributes: outpin, to switch the lamp on or off; inpin, to check the correct function of the lamp, that it is lit when switched on; an attribute color, to define the color of the lamp; and a variable state that stores the state on or off of the lamp. If you now take a closer look at the variables of the lamp, you will quickly notice that outpin, inpin, and color are constant and only state changes at runtime. From code view, however, all four attributes are mapped equally within the class structure and land with an initialization together in the RAM. Particularly with embedded applications, which are coupled to high numbers of items, very small target platforms are used for cost reasons, which have strongly limited resources such as memory. Usually, the dynamic memory RAM is the biggest limiting factor, and the goal is to store constant data in ROM. How this can be achieved in combination with the Rhapsody and the RXF is shown next. In order to be able to store the constant data of the class lamp, now in the ROM, these must be pulled out from the class structure. This is done by applying the const object attribute stereotype to the constant attributes of the class, or by right-clicking on an attribute with the change to const object attribute. The result of the code generation now looks like this. The constant attributes have now been swapped out into their own structure, and a pointer to this structure has been added to the actual class structure. How this pointer and the structure with constant attributes can be initialized for an object of the class lamp will be shown in the next section. The assignment of the individual constant values is done via an instance specification. By right-clicking on the class, such an instance specification can be created with the option Make an Instance Specification. An instance specification shows the inner structure of a class with its attributes, associations to other classes, and their parts. An instance specification has no effect on code generation. What is still missing is a dependency on the created instance specification with the stereotype specify. This can be either from the corresponding class or from a global object that is of the same type as the instance specification, or from an object that is part of a file or singleton. In the following example, there's a dependency from the traffic light class to the instance specification. The now generated code for the traffic light class is now completed as follows. With the C file of traffic light file, static constant variables of type lamp const object data are created for each part, red, yellow, and green. The predicate const ensures that the data is not stored in RAM but in ROM. These are then set to the const object data attribute of the lamp class with the init realization operation of the traffic light class for the individual parts. This is done before the constructor calls to the individual parts, so that the constant data is already accessible within the constructor execution of the parts. Since no initial value was specified for the constant attributes in the instance specification, the default unspecified value is set in the code for each attribute. This can be set within the instance specification for the individual attributes in the value field of the feature dialog. After new code generation, the values from the instance specification are used for the initialization of the const variables. Here it's now nice to see that each object of the class lamp is initialized with different const values, and these are nevertheless in the ROM. Now the existing example is extended by another layer, namely a crossroad. A class crossroad is added, which, as the picture of the intersection shows, has four traffic light objects as part. The class traffic light has, as already known, three parts, red, yellow, and green, of the class lamp. In addition, the traffic light class receives two constant object attributes. One is the type to identify whether it is a car or a pedestrian traffic light, and the ID to uniquely identify a traffic light. Here it quickly becomes clear that even with such a small example, the number of const attributes can quickly skyrocket. As a result, it quickly becomes confusing and difficult to navigate, as the fully unfolded instance specification shows. The following helpers provide a remedy here. On the one hand, it is possible to call the populate for const data attributes helper by right-clicking on an instance specification. This deletes all model elements, such as associations or normal class attributes, from the instance specification, so that only a structure with all constant data attributes remains, in which one can navigate more easily. Furthermore, this helper can be used when a new const attribute is added in the associated class of an instance specification. This is then automatically added to the instance specification by executing this helper. Another helper is modify all const data attributes, which also applies to an instance specification. With this helper, all const attributes are displayed compactly in a list in a new window. In this list, the values of the individual attributes can be edited and then transferred back into the model. Values that have already been edited are displayed in bold to make changes traceable. With a large number of const attributes, a filter can also be very helpful here to display only a small section of the list. But sometimes you want to be able to change constant data at runtime. For example, during a debug session with the IDE. Now if the data in ROM is constant, this is not possible in most cases. For such cases, you can turn off the const flag during code generation with the move const data to RAM stereotype on the instance specification. If the move const data to RAM recursive stereotype is selected, all datasets that are hierarchically below the instance specification are also moved to RAM. In summary, with the use of a few stereotypes, the data of a class can be easily transferred from RAM to ROM to configure your application. Furthermore, the initial values of the data can be maintained and administered now simply over a helper. With this approach, it is possible to store all configuration data of an application in an instance specification, and thus to summarize the configuration of the application at one point. The features for Rhapsody presented here are only available in connection with the RXF from SodiusWillert and are not part of a normal Rhapsody installation. Thank you for watching, and feel free to check out the other videos on our channel.